definitions and, let's say, first examples. So first of all, the setting. I'm in the complex category. Which means that the object I'm looking at are complex manifolds, and all the maps I'm considering are holomorphic maps. So actually, when you work in this category, it's interesting sometimes to enlarge the category, and instead of looking at manifolds M, it's also good to allow singularities, complex spaces. I'm going to say a few words about this. So these two categories actually go together. Even if you want to study smooth manifolds, you have at some point to study also complex spaces, which is like a manifold, but you allow some singularities. So let me begin by a definition. If we take a manifold, complex manifold, we say that it is Stein when two things are true. The first is that M is holomorphically separable, and the second one is that M is holomorphically convex. Holomorphically convex. So I'm going to give the precise definition, but already I can say that this, in a sense, is to say that M has many holomorphic functions, and this, in some sense, is to say that it doesn't have too many holomorphic functions. So maybe a little bit of notation. I will write O of M. This is the set of functions, and when I say functions, I mean set of functions, and for me, function has scalar values. Function is scalar values, as opposed to mapping, where it can have value in any manifolds. Holomorphic functions, yes.
Can I ask you some questions?
Sure.
What does it mean to say something is holomorphically separable?
It's a good question, and I'm going to answer now. So we say that M is holomorphically separable. So let's say this is 1, this is 2. 1, when, if you take 2 points, let's say P and Q in M, there exists necessarily a function, a global function, holomorphic, such that the function can separate the 2 points, that is, send them into 2 different values in C. So a typical non-example, a counterexample of this is, let me begin by a non-example, the most typical non-example of holomorphically separable manifolds is when M is compact. Okay, so when M is compact, if you take 2 points, I take a global holomorphic function, so I have M, a compact manifold, and I take F, a holomorphic function, then it's easy to show that F is actually a constant. F is actually a constant. It follows from the maximum principle. If you suppose that you have a global homomorphic function like this, then somewhere there is a maximum, and you just have to look locally here, and you see that necessarily it is constant locally, and then by analytic continuation, it will be constant globally. So in a compact manifold, there are very few holomorphic functions. Okay, essentially, the set is only constants. So it will not separate points. It will not separate any pair of points. Now, a typical example of holomorphically separable manifold is an open subset in Cn. typical example. M equals omega, so I'm going to denote omega for a domain in Cn. So domain means open and connected. So this is holomorphically separable. Okay. On Cn we have the coordinate functions. We have the coordinate functions z1 up to zn, and I can look at this as global holomorphic functions, well, on Cm or on omega, and saying that I take two different points on omega is just saying that there exists some coordinate that will not match. So these functions actually are separating the points. Okay, if you want, this is the projection on the axis. So the domain in Cn is always holomorphically separable. I would not insist too much on this holomorphic separability. I think the other part is more interesting. It's a more subtle notion. As the holomorphic convexity. Let me give you the definition. So there are many ways to describe a holomorphic convexity, and I will say it like this. If I take, so M is holomorphically convex if and only if I take a sequence of points in the manifolds that has no accumulation point with no accumulation point or no cluster points in M. So what does that mean? That means that topologically the sequence is tending to infinity. If you fix a compact, then after some rank, all the terms are outside of this compact. This is true for every compact. For every such sequence, there exists a global holomorphic function such that the function explodes on this sequence. So I would say like this. This tends to infinity when n tends to infinity. So that's one definition of holomorphically convex. And this is related to the previous talk because this is equivalent to pseudo-convex. This is one of the many definitions of pseudo-convex. Let me give you a few examples of this. So, example, I can take omega and open set in C. If I take omega and open set is in C, so maybe omega looks like this. I don't know, maybe it's not bounded. So this is omega, maybe it's not bounded, maybe it's not simply connected. This is an open set in C. So I take a sequence in omega that has no accumulation point. So maybe if omega is not bounded, the sequence itself has no accumulation point. Then to find a function that satisfies this, it's very easy. You just take the identity and you get what you wanted. Another possibility is that the sequence of points maybe is converging, but converging to a point that is on the boundary. We can also find a function. So if this boundary point is called W, then we have a sequence of points Pn tending to W, and we want a holomorphic function on omega that is going to explode when we apply the Pn's. and we can take, what do we take? 1 over z minus w. So if we do this, this is a holomorphic function on omega because w is not in omega, so no problem. But the pn's, of course, tend to omega, so this tends to 0. So that explodes. And I just showed that any open set in C is holomorphically convex. Okay? That is the full proof. But this is very special to dimension 1. Now I'm going to give the main fundamental non-example, and this will be essentially the same as you gave earlier. So, fundamental non-example. So this example of a non-holomorphically convex domain is very important. It was discovered, I think, beginning of the 20th century. And I guess that a big part of the field of several complex variables is actually related to the existence of such an object. So this example is in C. Is in C2. Well, it's what is important here is that we are in Cn with n at least 2. This is what is important. It's not the C2, is that we're not in dimension 1. And this is the example. I'm going to draw a picture, or maybe some notation. This is the picture. And I'm going to denote delta R. It will be a product of two disks. So I will write Z1, Z2 in C2 such that the modulus of Z1 is less than R and the modulus of Z2 is less than R. So it's a product of two disks of same radius R. And I will define omega as this bidisk minus the closure of a smaller bidisk that is contained in this one. So this is a diagram where I can draw the modulus of Z1 and the modulus of Z2. And I can draw a very accurate picture of this domain. Omega looks like this. 1, 2, 1, 2. And now something very, very special happens. Is this fact I'm going to prove quickly. Any function that is holomorphic on this omega extends as f holomorphic on all of the bigger polydisk. That is, a priori, it's just defined and holomorphic here, but then necessarily it extends as a holomorphic function everywhere. So let me give a quick proof of this, maybe very quick. I will just give the idea. So proof, almost proof. Such a function can be written as a series that looks like this. It's like a power series, but we allow negative exponents as well. It's called a Laurent series. And it is not difficult to see that a holomorphic function on omega can be written globally as a power series, this Laurent series. So this series, this way to write the function is valid for every z1, z2 in omega simultaneously. It's one series for everybody. Now, what do? We can rewrite this. I will group the powers of z2. So I will take a sum over j of the sum over I of a ij z1 I z2 to the j. So this is for z in j and for I in z, j in z and I in z. Now if I take a point, so I fix a z1. I fix a z1 whose modulus is between 1 and 2. I fix z1 and I look now I fix z1 with z1 in modulus between 1 and 2. So I am somewhere here. Okay, the z1 is somewhere here. And then I look at this function, z2 maps to f of z1, z2. So this is a function of one variable. And it is well defined for z2 in the whole disk of radius 2. I can go down. The variable z2 is allowed to vanish here. But if the variable z2 is allowed to vanish, it means that, so I have the power expansion of this function that is written here. And because z2 is allowed to vanish, then necessarily there are no negative exponents in this Laurent series. For every j negative, this must be 0. But if for every negative j this is 0, then I can also let z1 vary now. So for every j negative and for every z that is like this is 0. Okay? Now fix j negative, and when z1 varies, what is here is actually a holomorphic function of z1. But if this is a holomorphic function of z1 that is identically 0 when z1 is in there, then necessarily it's identically 0 everywhere. So this will be 0 everywhere. So this shows that in this series, actually, let me go back to this series. I don't know, but j cannot be negative. But actually this is completely symmetrical, so I can do the same reasoning to show that this is also non-negative. Yes, I can include 0. Non-negative. Yeah?
Use a different definition of nature than this.
Yeah, there's a two competing definition in the history.
Non-negative, right? If I say non-negative?
I mean, when I use both things n, I usually use it for natural numbers 1 to 3. Not
Oh, really?
Yeah.
One? Include?
But there's a,
Okay. Okay. For me, I use n star for this.
Oh,
I use n star if I want to exclude 0. Okay.
yeah, but there are two conventions for n. One of them is yours, another is...
Okay, actually I didn't know. For me, I include 0. I include 0. Okay, so this is the proof that any function extends. So this is really a fundamental fact of several complex variables, is that you have this extension of functions. So this has no equivalent in complex analysis in one dimension, in one variable, and this has no equivalent at all also in smooth geometry, infinity manifolds. No equivalent. This is very special to several complex variables. Okay. So these are main examples, especially for domains in CN. Now I want to look at the definition of being Stein from a different perspective. And I want to convince you that, oh, I shouldn't have deleted this. I want to convince you that Stein is a very natural notion, a very natural concept. So I want to give a, in some sense, natural definition of Steinness. So in many parts of geometry, when we have a geometric object, we consider an algebra of functions. Maybe I want to use a special letter, yeah, maybe like a curly A. So we like to associate to a geometric object an algebra of functions. So depending on the category we are, the relevant algebra of function will vary. So let me give you a few examples of what I want to talk about. So this is, I would say like this, topological algebra. Topological algebra of scalar valued functions. I want to insist that this is scalar valued functions. So for example, if K is a compact topological space, then we associate the algebra A of, so this is the case where X, I take X to be this, then AX will be C0 of K. So this is the algebra of continuous functions on a compact topological space. But I want to add some structure. I want to talk about this as the normed ring of continuous functions. Now in another category, if we take X to be, let's say, M, C infinity smooth manifolds, then we can do something similar, but this time we want to associate the algebra of C infinity functions. Okay? And again, I want to put some algebraic, some topological structure. Let's say again, normed ring of smooth functions. Let me take another example. When X equals V, and this is an affine algebraic variety, then also in this category, it is very classical to associate A of x, which in this case is denoted K of v. And this is, let's say, the algebra of polynomials on the variety. Now, in these three categories, it is a fact that when we have the algebra of functions, we have the geometric objects. So here is very classical. Okay. Algebraic geometry, fine. It's the same as commutative algebra. And here it's also true that if we know this object, then we know this one. And in this case, it's true as well. So I think this is very remarkable. It's not very practical. I don't think this is very useful in practice. But here, I want to insist a little bit. I take a compact topological space. The object I associate to it is the ring of global functions. And the only thing I'm looking at here is that I have a normed ring with some algebraic structure. And what I'm saying is that just the algebraic structure of this set determines completely the topological type of this. I think this is very remarkable. Here, when I look at this, I don't even know that this algebra is an algebra of functions. I completely forget this. It's just an algebra with some structure. But the algebraic structure of this, with a little bit more, it must be looked at as a topological algebra. It completely determines the topological space. So
what is the norm, the ring of smooth function you're talking about over here?
Here, so I want compact
norm
here.
you take.
I want compact, smooth,
The norm you take.
compact. The uniform norm,
Oh, okay.
compact.
So, compact open compact.
So yes, but I don't know if the theorem is still true if I take non-compact and compact open topology. I cannot guarantee. I don't know. It could be, but I don't know. I'm not sure.
What is the uniform norm? Can you define the uniform norm?
It's compact when they take the supreme
It's compact. So if I
Maximum or
supreme
of over all derivatives?
no.
It's infinity you're talking about, right?
We can do so, but maybe.
No. Here I
Well,
think
you have to
for
converge to C infinity.
I guess
So you have to take the supreme all derivatives,
we can ignore
which can be really.
no, I think you don't have to. I cannot guarantee, but I
Oh,
think
you don't care completeness. You just
No.
only want a norm.
yeah. I think
Your
that's enough.
algebra is not complete.
I think
Under the norm.
yeah, and I think it's enough.
Okay.
I think it's enough. Just
Well, then just
so
take
the same. The same norm as here.
So it's a sub-algebra of the.
Yeah, it's a subalgebra of
If
this.
it's the.
Yeah. But if you knew that it comes from a infinity manifold, then I think you can recover. Okay, so I want to say this, and I want to ask a similar question for complex manifolds. You can already guess what the answer is. So, when X is M a complex manifolds, the algebra we associate is this. The algebra of global Holmesque functions. Again, I insist that these are not sheaves of functions. It's not sheaves, it's just the algebra of global functions. There's much less information in that. My question, can we recover the manifold from this? Well, actually, in general, the answer is no, and we already know why, because, for example, if M is compact, we lose everything. Okay? So there's no general hope, and already from algebraic geometry in the room are laughing. It's stupid to try to do this, because compactness already completely ruins this hope. But what can we say? So, when can we recover M from this algebra with maybe some structure. So to explain this, I think there is a beautiful answer to this question. Let me introduce just a few words. Definition. A character is a continuous morphism of algebras chi from some topological algebra to C. So if I have a topological algebra, I define a character like this.
Do you write A of X or just A?
So I don't know. This is A, but of course my A will be the A of X. So you choose. I wanted to insist that I want to apply that.
Just any topological.
I need to apply algebra, but I want to apply that to my all this A of X. So this is A, but so this is what I call a character. Actually, I include continuous. And then spec of the algebra is the set of all characters. Now, with these definitions, I can say a few things. First, let me give you an example. Example of characters. So suppose we are in this case, we have a complex manifold, and we look at this algebra. So M and O of M as above, okay, complex manifold, and this algebra of holomorphic function. Then I can do this for any point P in M.
Oh, wait, so do you have a norm in those cases? In the case of complex manifold?
So actually, you don't have a norm, but yes, you have. This is Fréchet. This is a Fréchet space. Okay. So I will just say there is some topology in this. I don't want to give the details, and actually this is a Fréchet space, less than a norm, but a topology for sure. So an example of a character will come from just giving a point. Every time you have a point in the manifold, then you have what is called a point character, and it's very simple to define. It's just the evaluation. Okay, if I have a point, now I have the point given P. Now every time I have a function, I can evaluate the function. And this is a character. This is a morphism of algebras. And if the topology here is reasonable, this is going to be continuous. Now let's continue in the nonsense definitions. Define psi from M to spec of O of M, and every time I have a point, I associate the point character. Now with all this, I can go back to what I was talking about earlier. First, the remark is that saying that psi is injective, psi is one-to-one, is the same as saying that M is holomorphically separable. Now, for the case when M is a domain in some Cn, then saying that Psi is surjective is the same as saying that omega is holomorphically convex. So I did all these definitions. It was a bit long and it was not clear where I was going, but now I have a very nice definition for being holomorphically separable and holomorphically convex. Now we are very close to Stein. And in general, for M any manifold, it is a theorem that M. So, no, these are, if you want, either classical results and I didn't prove it, but this one is not difficult. This one follows from different. This one is difficult.
Oh, difficult.
Yes, this one is difficult. This one is really not obvious. Yeah, this one is just the definition actually. Now, for any manifolds, M is Stein, if and only if. This is a homeomorphism. So I need a little bit more than bijection. In general, I need a little bit more. So this is a classical result. Maybe it's people like Gawat and Heimert that proved this this theorem. So what I like about this is that it gives a very, very natural definition for being Stein. Okay? This is an alternate point of view. Again, it's not very practical, but philosophically, I think it tells a lot. It tells a lot. It says that being Stein is exactly saying that if you look at the algebra of functions and you work with functions, then you're not missing anything about the manifolds.
Is there an easy way to give the topology for this spec of A?
No, it's not so easy. No, so it's Fresher. It's a Fresher space. You can give a structure of a Fresher algebra, and it's nothing is too.
Okay. So in the homeomorphism is a homeomorphism between the manifold and the Fresher space.
So in the spec of this Fresher. Yeah. So there is one way to give. So this I didn't say anything. No, I don't want to say anything. There is one way to define a topology there, and then it's a homeo. But then you need a topology on spec. So on the algebra, you have compact. You can do compact open. Yes, it is compact open. But then you need a topology on spec, and then you need to work a little bit to see what is the good topology on this.
So it's not just a restriction.
Restriction of what?
Of the compact open topologies. No.
But the compact open topology is on the. Is not on the.
So we give we have a Fresher topology on. You said OM is a Fresher space.
Yes.
And so can we just regard the spec of OM as a subspace of the function spaces?
But this a priori, does it have a good topology? A compact open topology on this?
Yeah.
I don't know. I don't think so, but I'm not sure. Let me give now a completely different characterization of Stein spaces. It's a theorem that is due to Heimert and says that M is Stein if and only if it embeds holomorphically as a closed submanifold of some Cn. So I write a capital N. Maybe this capital N is big. So this is the similar to Whitney embedding. In a smooth manifold, any manifold can be embedded into Euclidean space.
So
Now,
Stein manifold has boundary? Also open Stein manifold or just Stein manifold is boundary?
no, my manifolds have never have any boundary. And
You
yeah.
embed that as a closed
Yes. So this is very confusing, but very interesting. This is confusing because I have, for example, given examples of Stein manifolds as domains, and now I'm saying that they embed as closed submanifolds. Yes, this is exactly what I mean. You say that even for a domain, for example, the unit ball in Cn, this is a Stein manifold, it is true, and by this theorem, it is possible to embed the unit ball of Ck into some Cn, but maybe this n has to be very big. And let me give you a so let me give you a theorem. Maybe I give you a theorem about the dimension, and I can give you also some open problems. So I think if you put together results of Eliashberg, Gromov, so this is 92, and also Schumann, 97. So this is older, maybe this is in the 50s or 60s, I don't know, 50s or 60s. And this is more recent. It is about what is the optimal n here. Okay, so similar to Whitney theorem, it gives the optimal embedding dimension, and they gave this following theorem: let n be at least 2, then all Stein manifolds embed in Cn with n equals this, n plus the integer part of n over 2 plus 1. And this capital N is optimal.
So that is the dimension of the Stein.
Yes. Let's see this. All Stein n manifolds embed into this. And this is optimal. Now there is something funny here, is that assume that the dimension is at least 2. And the case of n equals 1 is not trivial at all. And it is actually open. So, open problem. Does any non-compact Riemann surface embed in C2? So suddenly I'm talking about non-compact Riemann surface, but Stein manifolds of dimension 1 are exactly non-compact Riemann surfaces. These two sets are equal. So I prefer to say it like this. So you see, this is the case of dimension 1 of this theorem, and this is open. As far as I know, this is open. Another open problem, which is related to your question: what is the best n when m equals a ball or a polydisk in Cn. So this is really non-trivial. If we have even a very simple domain, maybe the simplest of all domains are the ball or the polydiscs. So we know it's not difficult to show that this is Stein, because this is holomorphically convex. So we know by the theorem of Remer that they embed. They embed in some Cn, and it is actually unknown to find the smallest embedding space for those as a closed subspace. And I think there are papers about very particular case already to embed the unit disk in C2. I think for the unit disk this problem is solved. There exists an embedding of the unit disk in C2, but already this is not easy at all. And then I think there's another paper about the unit disk minus 1 point. Again, to embed this into Cn, it's not obvious. So people do examples one by one almost for us. So it seems to be difficult. I'm no expert, but I find that really, really interesting.
Do you know the embedding of disk in C2? Can you write that down?
I think this one can be written explicitly. You find functions, and you use the functions to embed. And I think this is maybe is pretty old. Maybe this is due to Weierstrass or something like that. Maybe this is the only one that is old, and then all the rest is difficult, is 20th century, and
You mean football, this capital N can be less than that.
yes. Okay, this one is optimal if you consider a problem of embedding all manifolds. But if you restrict to a very simple manifold as the ball, then you can definitely hope to do better. And the optimal bound is not known.
So why is this optimal?
So there exists for each n, there exists a Stein manifold of dimension n that embeds in C to this power, but does not embed in C to this power. This is what I mean by optimal.
What will be that kind of manifold?
I don't know. I don't know. Yeah, I don't know.
Sorry, I'm still confused because you can embed that as a sole manifold in Cn, and then I think that implies there is a fully sum harmonic function whose Weber set is just boundary of the embedded one. So we should have some boundary. So closed, you mean closed manifold means closed manifold without boundary, or just closed manifold?
So manifold for me means with no boundary. Never any boundary anywhere.
I'm confused.
So yeah, what is?
I mean that implies the existence of fully subharmonic function whose Weber set is just boundary of the embedded one.
This?
Yeah.
No, here you
Closed doesn't mean there's a boundary. Closed simply means
so you see closed. So this is C to some power, and the closed embedding will.
Means the closed.
it's just
I see.
submanifold. It doesn't mean
So you don't have the defining function that is a place of harmonic.
There's no accumulation.
Oh, I see.
There's no accumulation point.
Oh, I see.
Outside of it.
Yes.
Well,
It is
yeah.
a definition of submanifold. All submanifolds are supposed to be closed in most of our.
So actually, yeah, most people, I insist here I write closed, but usually in several complex variables it's often all closed.
So that sole manifold may have boundary in that sole manifold.
No.
No, it has no boundary. It
Closed
has,
condition.
it has no boundary.
Anyway, closed makes sense. No, boundary goes to infinity. That's all.
Yeah, boundary may go infinity.
No,
Yeah.
Boundary has to go to infinity in this case.
Yeah. If you
Talking
embed,
about boundary, it's going to go to infinity in this
yes.
map. That's what it means.
Oh,
to be
yes,
closed.
that's right.
Okay.
Yes, that's one way. That's one way to say it. Yes.
Oh, I see. Okay, now.
All right, 5 minutes more.
Is this embedding actually a graph?
These embeddings?
You know?
No, you cannot
I
hope.
mean disk, even for disk.
I think even for the disk, I would expect it's not a graph, because I know that it's not easy. To embed the disk, the unit disk, it's not easy.
Yeah.
You have to work, so I suppose it's not a graph.
Okay.
Okay. So maybe I'm going to stop here.
So who did the embedding of the disk?
So maybe it's Weierstrass. I'm not really sure. I think for the disk, unit disk, it's very old. But that's the only result like this that is old. Maybe Weierstrass. I don't guarantee.
And it's complicated.
And I think it's difficult. And I'm pretty sure that already the disk minus 1 point, that is maybe second part of the 20th century already. This is this is difficult. And maybe people do to annulus and one by one. Difficult.
Okay.